Welcome everyone. This is separation processes course presented by me, Saiffulla. Today we are going to continue this topic, which is the multi-stage binary distillation. So we are still talking about the distillation, which is a separation process based on the difference in the boiling point temperatures, and we are talking about binary mixture that we have only two components. One is the light component and the other is the heavy component, and it is multi-stage, so we have more than one stage, or in other words we have a column that contains many stages. Okay, and again we are talking about stages, so we are talking about the equilibrium based model where we assume that each stage reaches the equilibrium. And today we are going to continue the McCabe Thiele method, and this will be the last video covering this method, which is the McCabe Thiele method, which is a method used for distillation for the binary mixture, and of course it is multi-stage distillation. What we are going to talk about today, actually we are going to cover three topics. We are going to cover three topics. The first topic that we are going to talk about the minimum reflux ratio, the concept of the R minimum or the minimum reflux ratio, and then are going to talk about special cases of distillation column where we have multiple feeds, so we may have F1, F2, etc. until the Fn we have too many feeds, and we are going to cover the case where we have a side stream S, could be S1, or we have two side stream, etc. And we are going to talk about a case where we don't have a reboiler, and instead of it we are using an open system steam, and we are going to talk about it in this video. The last thing that I want to cover is the concept of efficiency, how we can use this efficiency in order to get an actual results, and we are going to talk about it a little bit more, and uh, and to distinguish between the overall efficiency and the plate efficiency, as we will see inshallah. So let's start talking about the concept of the minimum reflux ratio. Uh, the minimum reflux ratio usually it is convenient to determine the reflux ratio in terms of the minimum reflux ratio multiplied by some factor here, for example 1.1, 1.2, etc. So it means that this minimum reflux ratio we need to work above it. We cannot work at this minimum because it is the minimum. It's the minimum that we cannot work at. We need to work at a reflux ratio that's higher than this value. So this C will be greater than 1, of course. Okay, so for example, if we say that we are working at a reflux ratio that's 60% higher than the minimum, okay, so this means that the R is equal to the minimum and higher than the minimum, so plus 60%, which is 0.6 R minimum. And if you take a common factor, you can see that R is equal to 1.6 R minimum, so this number C is greater than 1 always, as that we need to work at a reflux ratio that's higher than this minimum reflux ratio. But the question here is that why we want to avoid this minimum reflux ratio, and why we want to work at a reflux ratio that's higher than this minimum reflux ratio. Why is that? What's the concept of the minimum reflux ratio? Okay, to explain this, let's draw a McCabe Thiele diagram. For example, we have a specific separation process, and Then we try to analyze this process using the McCabe Thiele method. And for example, this is the 45-degree line, and we have, for example, this equilibrium curve. And then we have, for example, this is the the composition of the feed. Okay, and this is the Q line, for example, and uh, we have, this is the top section operating line, which start at XD, and we have this is the waste composition, so this is the bottom section operating line. And then after drawing these lines, as we discussed in the previous video, uh, we then we're gonna count the number of stages, right? Starting from XD, we go until we hit here, one stage, second stage, and this is third stage. Okay, so as you see, we have here we have 3 stages. But what will happen? Just imagine, see this red line, see that red line, this red line, which represent the top section operating line. What will happen if we move this line upward? Okay, what will happen if we move this line upward? Let's see what will happen. Let me remove this. What we're gonna do is that we're gonna move this deadline. It was like this. Let us move it up, so in such a way that it becomes like this. Sorry. So we just move this line up. In other words, it was like that, and then it becomes like that. Okay, in other words, this has a high slope, this has a lower slope. Okay, so we lower the slope of this top section operating line. What will happen is that if you draw the other lines, for example, this is the Q line, and this is the bottom section line, what will happen is that when we start counting the number of stages, see, so this is the first stage, the second stage, the third stage, and then we stuck at this point. We stuck, we cannot move. Okay, we cannot move, and what will happen is that you are going to get an infinite number of stages, which is not practical. And how this become, let's focus on this point. I'm going to draw this on another page. See, this is the point where we stack. Okay, so this is just a point. I'm just zooming it. I am zooming this point where we get stacked. Okay, so what will happen is that we are, see, we was here, start counting the stages until we reach this point. C, we are not going to move. Why? Because if you move left, you hit the equilibrium curve at this point, and then you move down, you're still at the point. See, still at the point, you cannot move out of this point. In other words, there will be an infinite number of stages, which is not practical. You cannot have infinite number of stages at your distillation column in order to achieve a specific XD. Okay, so that's why we want to avoid this condition. This condition will happen at a value called R minimum. This R minimum will cause this condition to occur. Okay, And if you are interested how they determine this minimum value, they do a sort of experiment. They take this distillation column, and this is the condenser, and then instead of taking a product stream, no, they remove this product stream and reflux all of the product, so in such a way that we have zero distillate. We don't have any molar flow rate for the distillate, and you know that R is equal to L over D. So if this D is 0, R will go to infinity. Yes, because 1 over 0 is infinity. Okay, so that's why it is called the minimum reflux ratio at the infinite reflux. So we have an infinite reflux. In other words, we have a total reflux. And then they measure this reflux, and this will be called the R minimum. This will be called the R minimum. Okay. And after they measure this, this will cause this stack where you have an infinite number of stages. That's why we avoid working at this R minimum, and we choose a value of the reflux that's above this R minimum. Okay, this is the concept of the R minimum. The question here is that how we are going to find this R minimum graphically instead of using an experiment. Can we find it graphically? Yes, we can. How we can find it? We can find it again using the McCabe-Thiele method. The McCabe-Thiele method, we can use the McCabe-Thiele method in order to determine this R minimum graphically without doing this experiment. Okay. How we are going to determine this? Suppose in a given question, you draw this axes with the 45-degree line. Of course, this is the x-axis, which is composition in the liquid phase, and this is the y-axis, which is the composition in the vapor phase. And then suppose that you have Q is equal to 1. So as we discussed in the previous lecture, if you have Q equal to 1, so at the feed, at the composition of the feed, you will have a vertical line, isn't it? Yeah, and suppose you are given this equilibrium data, or you are given the value of alpha, so you can construct this, and then you draw the equilibrium curve, and got this you got this equilibrium curve. Then how to determine this R minimum? Actually, we have two situations. Okay, we have two situations. The first situation is that we have an equilibrium curve like this. Okay, when we have an equilibrium curve like this x-bow, okay, what we are going to do, we are going first, the first step is to determine where is the xd. For example, if xd is equal to 0.9, so you go here 0.9, this is 0.9, so it is here is your xd. Okay, and then what you are going to do is that you will draw different lines. For example, see this line, and this line, etc. And then you're gonna see which line is intersecting this equilibrium curve, which is the purple curve. Which line is intersecting this equilibrium curve and intersect also this Q line curve if it is extended. Okay, so let's extend this Q line. Let's extend this Q line until we reach the equilibrium curve and see which line is intersecting this Q line and the equilibrium curve, and it originates from this XD. Is it the first line or the second line or the third line? As we can see, it is the third line. So see this line, the first one, it is intersecting the equilibrium curve and the Q line curve at this point. So this will be the line that I'm going to use to determine the R minimum. Okay, and then I extend this line and see the intercept here. Suppose that I got an intercept value of, for example, 0.6, just for example. Okay, then remember this is the operating line, the top section operating line, and remember from the previous lecture that we got this equation for the top section operating line, that's y is equal to r over r plus 1 x plus xd over r plus 1. So if you see here this green lines, which shows the first green line, these lines are nothing but the top section operating line. So this intercept here will be this, which is xd over r plus 1. Okay, so I will read the value here if it is 0.6. So just take this 0.6, this is the value of the intercept, and then equate it to this intercept, xd over r plus 1. Okay, and if we have, for example, an xd value of 0.9, okay, and since this intercept is at the minimum condition, so this will be the R minimum. Okay, so you can use the solver to get this value, having this value of xd and this value of the intercept. So this is the way to determine the minimum reflux ratio. Another situation is that when you have an equilibrium curve like this, see, it is some distorted equilibrium curve. It is like this. Okay, and then this is the 45-degree line. Okay, and suppose that you have this is ZF and this is the Q line. What will happen here? Suppose that you have xd is equal to 0.9, so it is here. Here is your xd. What will happen is that if you draw different operating lines, you see there is no line that intersect this Q line with the equilibrium curve. Okay, there is no line that can do this for me. And if there is, see, if there is, for example, if we have this line, what will happen is that I cross the equilibrium curve. And this cannot happen. You cannot work outside this equilibrium curve because equilibrium is the maximum condition that I could reach in the ideal situation. Okay, so what will happen is that I cannot work I cannot work outside of this equilibrium curve. So how to determine the R minimum? To determine the R minimum, simply I will look for a curve that only touch this equilibrium curve. See, it touched it at this point. And since it touched this equilibrium curve, I cannot go above this equilibrium curve. So this line will determine the R minimum value. This line that intersect with the equilibrium curve, it touched the equilibrium curve, even it is not even it is not intersecting with this point, which is where the Q line intersects with the equilibrium curve. Because it's touched this equilibrium line, it's fine. This will determine for me the R minimum at this intercept. And why? See, if we try to draw the stages again, we will get stuck here at this touch point. Okay, so we will need an infinite stages. In other words, we will have the minimum reflux ratio at this condition. Okay, so for example, if you take the intercept here to be 0.5, again you will say that 0.5 is equal to xd over r minimum plus 1, and if xd, for example, is 0.9, if xd is 0.9, so you can determine the r minimum value. So we have two situations. If the equilibrium curve is good, it is like an x-bow. Okay, so we can only draw a line that intersect with the q line and the equilibrium curve, and then take the intercept to determine the r minimum. The other situation, if we have this bad equilibrium curve, so it is enough only to touch this equilibrium curve to determine the r minimum value at this intercept. Okay, so these are the two situations. Now let's take the opposite case where we want, for example, to determine the minimum number of required stages, the n minimum, the minimum number of required stages. What we're gonna do is that we are going to draw this equilibrium curve and then draw the 45-degree line. Okay, and then determining the xd point. Okay, and what we're gonna do, we are going to assume that the operating line coincide with the 45-degree line. This, for example, if you say that this green line is the operating line, it will coincide within the 45-degree line. See, the 45-degree line is this purple line, so it will coincide with this purple line. The operating lines will coincide with this purple line. At this condition, you will have the minimum number of stages. See, if you draw the stages starting from xd to xw, for example, if here your zf point, see, then you draw these stages. Okay, assuming that the operating line coincide with the 45-degree line, you're gonna get the minimum number of stages. Why you're gonna get the minimum number of stages? See, because if you try to move the operating line up and get far from this 45-degree line, what will happen? See, what will happen if we move this green line, if it does not coincide with the 45-degree line, for example, if it is like this, and then this is the ZF, and then you have something like this, what will happen? See, when you count the number of stages, you will hit the equilibrium curve a lot, so you will get too many stages. Okay, that's why as you move the operating line down until it coincides with the 45-degree line, you will get the minimum number of stages, because you're gonna hit this equilibrium curve less. The times that you're gonna hit this equilibrium curve will become less. Okay, that's why you will get the minimum number of stages, the minimum. And as you move this operating line up, as you see the purple stages, you're gonna get too many stages. Okay, you're gonna get too many stages because you're gonna hit this equilibrium curve a lot and a lot. Okay, this is the concept of determining the minimum number of stages. And now the second thing that I would like to talk about is that the case where we have multiple feed, we have side streams, and when we have an open system. Okay, so let me talk about the first case where we have too many feeds. We have multiple feeds. In this case, how we're gonna deal with this? It is like this. See, let me draw. this is the distillation column, and then this is the condenser, and then this is the reboiler, and you have here the distillate, you have the waste with X waste, you have the distillate with XD. Instead of having only a single feed, we will have, for example, 2 feeds, 3 feeds, 4 feeds. Okay, we will have more than one feed. Okay, so let's call it F1, the first feed, and this is F2, which are the molar flow rates of these feeds. And let us call the composition of the light component in the first feed ZF1. So this one refers to the first feed. It is not referring to the component 1. No. When we say ZF1, this means the composition and the feed number 1 for the light component. And again, ZF2 is the composition and the composition of the light component in the second feed. Okay, and then what we're gonna do is that, remember that we say when we have a normal distillation column with only one feed, we're gonna divide the distillation column into 2 sections, the top section and the bottom section. Okay, and what we're gonna do here is we're gonna do the same idea. We're gonna divide the distillation column, but since we have 2 feeds, we're gonna divide the distillation column into 3 sections instead of 2 sections. So this will be my first section until feed 1, and then this will be my second section until feed 2, and this will be my third section from the feed 2 to the waste. Okay, so the idea is that we're gonna only divide the column into 3 sections. Each section is separated by a feed stream. And you can extend this idea. For example, if we have 3 feed stream, we're gonna divide our column into 4 sections. If we have 4 feed streams, we're gonna divide our column into 5 sections. Okay, and the most important point here is that each section will have its own value of liquid and vapor flow rates. Okay, why? Because this feed is gonna change the flow rate of either liquid, vapor, or both, depend on the Q value. Okay, and we will have here Q1 and Q2 for each feed stream, which represent the amount of liquid in this feed. Okay, so for example, if we have in the top section the liquid is 100 kilomole per hour, if this feed is saturated liquid and at 50 kilomole per hour, so this 100 kilomole per hour will be added to this 50 kilomole per hour, and then the liquid in the second section will be different. Okay, so I can call it L prime, for example, and this will be V prime. So if I have a vapor in this feed, for example, I have a Q equal to 50%, so this vapor also will be affected by this feed. That's why we divide our column into sections separated by the feed streams. And again, for the last section, it will has its own L and its own V. Let's call this L dash and V dash. And how we gonna deal with this problem, and how we gonna use the McCabe Thiele method in order to analyze this type of distillation column? The idea is simple. Is that, remember before, when we have one feed, we have 2 sections, so we have 2 operating line and we have 1 Q line, right? That change, we have 2 operating line, one for the top section and one for the bottom section, right? The idea is that if you have 2 feeds, you will have 3 sections. So you will have, instead of only 2 operating line, you will have 3 operating line for the top section, middle section, and bottom section, for all sections. Okay, and since you have 2 feeds and each feed has its own value of q, okay, so you will have again 2 values of q, so you will have 2 q lines. Okay, so this is only the difference. Okay, and again, if you have 3 feed, you will have 4 section, you will have 4 operating line, you will have 3 q line for each feed. Okay, and remember the equation for the top section or for the bottom section. The equation either for the top section or the bottom section, remember the slope was L over V. The slope was L over V, right? So this is the slope. Okay, so this means that each section, since it has its own value of L and V, for example, the first section has L and V, the second section has L prime and V prime, the third section has the L dash and V dash. Since each section will has his own value of L and V, so the slope will be different for each section. In other words, the slope of each operating line will be different depend on the value of L and V. Okay, and how we gonna determine these values of L and V? We can determine them using a simple material balance around each interface between any 2 sections. So this is the first interface and this is the second interface between the 2 sections. So let's, for example, take both will have the same idea. So let's consider the first intersection, for example, and we can zoom it. So if we zoom this intersection between the 2 sections, see, if we zoom it, so this will be the intersection. We will have here the feed 1 with ZF1 and Q1. Okay, and we have liquid going down from the top section, which is L, and vapor going up from the top sections, which is V. And then for the bottom section, so this is the section number 1, the first section, and this is section number 2, which is the second section or the middle section. Okay, and again we have a liquid going down and we call it L prime, and in this section again we have vapor going up and we call it V prime. So how to determine, for example, if we know the slope here, which is we know L over V, okay, we know the slope, for example, of the top section as we discussed in the previous video. And for example, if we do an overall material balance, we can, for example, determine the D, we can determine W, and if we are given R, we can determine L, and using the slope, we can get V. If we have this at the end, if we know the values of the L and V, how we can determine the values of L dash V dash? So if we know L dash and V dash, we can determine the slope of the second line, because the slope is simply L over V for each section. So the slope of section 1 will be this L over this V. The slope of the second section will be this L over this V. So in other words, we need to determine L dash and V dash in order to determine the slope. And once we determine the slope, we can draw the operating line for the second section. Okay, so how we can determine this? We can determine this using a simple material balance around this interface and assuming a steady state, so N equal to out. And for example, if we want to look at the liquid, okay, so we have 2 inlet of the liquid. This is the inlet 1, the liquid coming from the top section, plus the fraction of liquid in this feed number 1 is equal to out. What's out here is the liquid in the bottom section, which is L prime. Again, for the vapor, let's do the same thing. For the vapor, we have two inlet of the vapor, which are V dash and 1 minus Q, the fraction of the vapor in feed number 1, is equal to the outlet. What's the outlet of the vapor? It is here, which is V. So if we know V, F1, we know L dash F1, and we know Q1, this is actual Q1 because it is the first feed stream, we can determine L and V using these two equations. And once we determine, sorry, not this V, not this L, we can know this L prime and V prime of the bottom section. Once we know them, we can get the slope of this section. But be careful here. One thing that I want to mention, when you do the overall material balance, that make sure you have two feed stream. Okay, so you need to say this. If you do the overall on this all three sections, you're gonna say that F1 plus F2 is equal to D plus W. Don't forget to mention that we have F1 and F2, and again we have the component material balance. ZF1 plus ZF2 F2 is equal to XDD plus XWW. Okay, so don't forget to add the both feed streams. Okay, so once we know L dash and L prime and V prime, we can determine the slope of section number 2, which is L dash over V dash. And once we know the slope, for example, let's say you got the slope. Just for example, let's say you got the slope is equal to 2. Okay, so you would say that the slope is y2 minus y1 over x2 minus x1. Okay, and what is y1 and what's x1? This we will see using the chart. Okay, so let's do the chart, the McCabe Thiele chart for multiple feed. So we will start drawing the 45-degree line, and then we want to draw, and then we want to draw the equilibrium curve. Suppose you have an equilibrium curve like this, for example, and then the first step is that you're gonna determine where is your XD. For example, if your XD is here, so just write here, this is XD. For example, if it is 0.9, of course this is X and this is Y, and then you need to determine where is your ZF1 and ZF2. For example, if it is here, for example 0.7, so here will be the ZF1, and then for example if ZF2 is 0.4, for example, so it will be here ZF2, and then you need to determine XW. For example, if it is 0.1, so it will be somewhere here, for example. Okay, so you need to determine XD, XW, and not only one ZF, no, you have two ZF, ZF1 and ZF2. Okay, now the second step is to draw the Q line. You need to draw the Q line, and since we have two feet, so we have two Q line. Suppose that the Q1 is equal to, for example, suppose Q1 is equal to 1 and the Q2 is equal to 0. So we have saturated liquid in the feed number 1, and we have saturated vapor in the feed number 2. For saturated liquid, you know that the line gonna be vertical, as we said in the previous lecture, and for saturated vapor, the line is gonna be horizontal, like this, and then you're gonna draw the top section operating line as we discussed in the previous video. Okay, so suppose you draw this top section operating line and you got a line like this. Now the question here is how I can draw this line, the second operating line for the middle section. Do we have a direct equation with slope and intercept that can help us to draw this line? Actually, you can derive it, but it is gonna be wasting of time. There is an easier way to draw the operating line for the second section. And what's this way? This way is to use the slope value. So the way is first to do material balance on the interface, and then you get L dash and V dash, and then after getting L dash and V dash you divide them, and then you get the second slope. Once you get the second slope, for example, if it is 2, then you determine y1 and x1. What are y1 and x1? They are here. See, this point, you read, here will be y1, here will be x1, then substitute them here. That's it. And then choose any random value for x2, for example. Choose x2 somewhere here, for example, choose it, for example, 0.5, and then substitute it here, and then determine y2. So if you choose x2 to be here, 0.5, and then you find y2 using the equation, for example, if you find y2 here, for example, then just what you have to do is that you connect these 2 points, the x1 y1 point and x2 y2 point. You connect them until you reach the second Q line as it is extended. Once you reach the second Q line, then you stop and you draw the operating line for the last bottom section. It is easy, you just connect this point to the XW point, and that's it. You have 3 operating lines. So this is the first one, this is the second one, this is the third one. And each operating line has different slope. Each operating line represents a unique sections, the top section, the middle section, and the bottom section. And then the last step that we all love is that counting the number of stages. And it is simple. You start from XD. You start from XD here, and then you count until you hit 1, 2, 3, 4, 5, and you stop at XW. So this will be the first stage, the second stage, the third stage, the fourth stage, the fifth stage. Okay, and if you're interested to know what is the feed number 1 stage, what's the stage for the feed number 1, you see the Q line for feed number 1. Here feed number 1, here Q line, and it is inside the second stage. So the second stage is the stage where the feed 1 is going to be introduced. And if you are interested to know the stage for the second feed, so you see here, this is the Q line, this is the Q line of the second feed, and it is in the fourth stage. So the fourth stage is the stage where the F2, the second feed, is gonna introduced. Okay, and that's it. That's the case where you have multiple feeds. The second case is where you have side stream. So you have, this is your distillation column, you have a column, and you have a reboiler, and this is the distillate, this is the waste, and this is the feed. And the side stream is that you take another product somewhere from a specific stage and remove it from the column as a side product. Okay, and this is usually we do usually when we have multi-component distillation. So if you have, for example, benzene, toluene, alcohol, for example, ethanol, benzene, toluene, ethanol, water. So for example, you're gonna take from the distillate the ethanol, and then you're gonna take a side stream to remove the benzene, and then the bottom stream, which is the waste stream, is the toluene, and that's it. So sometimes we need to deal with this situation. So let me call it S and the composition XS, which is the composition of the more volatile component and the side stream. How we can deal with this situation? Again, it is same idea. Since you're gonna divide your distillation column into some sections, so this is the first section until the side stream, and then this is the second section until the feed stream, and then this is the last section. Okay, and each section will has its own value of L and V, L dash and V dash, and L bar and V bar. Okay, so each section will has its own slope, but the difference here is in the material balance only. That's the difference, but the procedure is the same. So the material balance is only the difference. And how you can construct this material balance? For example, the overall material balance, you will say that F is equal to D plus W plus a side stream, and then F is equal to XD plus XWW plus XSS. Okay, that's only the difference, and also the difference will be at the intersection point. It will be difference. For example, not the intersection point, sorry, the intersection between two sections. For example, let's take this, let me do it on a different line, different color. So the intersection between these two sections with the side stream. Okay, so if we zoom here, if we zoom here, we will have something like that, where we have a side stream, and this is the top section, section number 1, and this is the bottom, the middle section, section number 2, and this is side stream with XS. Okay, and then you have liquid going down from the top section and vapor going up from the top section, and then you have liquid going down from the middle section and vapor going up from the middle section. So the difference will be only in the material balance. Okay, so if you consider steady state, so the material balance for the let's start with the liquid phase. Okay, of course this side stream again will have specific Q value, which represents the amount, the percentage of liquid in this side stream. Okay, so you will say that for the liquid you will have only one inlet liquid equal to the outlet. You have two, one from the side stream, so it will be QS, Q the percentage of liquid multiplied by the molar flow rate of the side stream, plus we have another liquid here at the outlet, which is L dash. Okay, and again for the vapor you have one inlet for the vapor, which is V dash, which is equal to 1 minus Q, the percentage of the vapor, multiplied by this S at the outlet, plus what else? We have also vapor here, outlet. So vapor, so this is a simple material balance, and again you can utilize this material balance to determine the values of L and V, and then you say that the slope of this operating line is equal to L over V, which is equal to y, which is equal to y2 minus y1 over x2 minus x1. And again you see, you draw the same thing you get from the chart, the x1 and y1, and then you take a value for x2 and get y2. So you have 2 points, you connect them, and that's it. This is the operating line of this section. Okay, So this is the case where we have a side stream. The last case is that where you have an open system steam. What do we mean by open system steam? When we say we have an open system steam, it is unique to a process where you have the water as your heavy component. So, for example, you have this distillation column, and then you have this is the condenser, the distillate, and this is the reboiler, and this is the waste. Of course, you have a feed here. Um, uh, so the case is that where if you have any component, so the light component is any component C, but the heavy component is water H2O. When the heavy component is water H2O, so sometimes it is better to for for energy recovery, which is the heat integration that has to do with the economical point of view, to reduce the cost of the plant or the cost of the process. We remove this reboiler, okay, and instead of this reboiler we use an open system steam. What do we mean by that? We mean that the column will be like this. This is again the feed, and we have the condenser, it will not change, and we have the distillate, and we will remove the reboiler and use an open system. What do we mean by that? We mean that we are going to introduce a steam from the bottom, a hot steam, so it will do the job of the reboiler. It is very hot steam, okay? And since steam is water, they are the same, but steam, it is in the vapor phase, okay? So we have the light component is any component, the heavy component is water, which is H2O, okay? So we are introducing steam here, so the composition of this steam will be zero. Why it is zero? Because when we say a composition, we refer to the light component, okay? So it is any light component, and since it is only steam that we introduce here, so the composition will be zero with respect to this light component, okay? And then we're gonna take our product here. This will be the waste with X waste, okay? So we don't have a reboiler anymore, and we call it an open system because you see the bottom of the column is open system. We have inlet and outlet. We don't have a closed loop like the case for the reboiler, okay? That's why it is called the open system steam process, and it's only used when you have the heavy component as water, okay? And what's the difference here is that only we have two differences. The first difference is the overall material balance. So the overall material balance will be F plus this open system steam. Let's call it for example, just for example, let's call it E. Okay, let's call it E, which is the molar flow rate of the open system steam. So the difference will be that the material balance will be F plus E. We have two inlets, the feed and the open system steam, is equal to, and how many output we have? We have the distillate and we have the waste from the bottom here. So it will be distillate plus waste. And for the component material balance, so we will have ZFF plus the composition E multiplied by E is equal to XDD plus XWW. And since we refer to the composition of the more volatile component, so XE, as we discussed here, will be always zero because we don't have any light component in this steam, the hot steam. So this will go to zero always. So we will have ZF is equal to XD plus xww, and the difference is that when we use the McCabe Thiele method, we will go with the same procedure, the same exactly procedure as the previous video. So we're gonna draw the Q line, and then we're gonna draw the top section operating line, the same, exactly the same procedure, but the difference is here. If you have, for example, xd is 0.9, so it is here xd, and zf is 0.5, so it is here zf. And for example, if you have xw is equal to 0.1, so for example it is somewhere here. In the previous video, when we have the boiler, what we do is that we just connect this point to xw here on the 45-degree line, right? The difference is that instead of connecting into here, we are going down here to the x-axis and then connect this like this until we reach the x-axis at xw at 0.1. For example, if we have xw 0.1, so instead of hitting the and stop at the 45-degree line, we're gonna stop at the x-axis, and then we count the number of stages in a normal way, like this: 1, 2, 3, 4, 5. That's it. So the only difference is that we're gonna shift this point down to the x-axis. And what is the reason behind it? Because understanding is always important. We need to understand the reason why we do like this in the McCabe Thiele method if we have an open system steam. Why? Because see, when you hit the x-axis, so let me zoom this. So you have this is the y-axis. Just I am zooming this point, and then this is the bottom section operating line, and then you hit this x-axis. What will happen when you hit this x-axis? See, this x-axis, once you hit it, this intersection, this means that you have a value of y equal to 0, right? You have a value of y equal to 0, and y is the composition in the vapor phase. And since we refer to the composition of the light component, and we know that the steam that we introduced in the bottom is vapor. So since it is vapor, it has a composition y. And since we refer to the light component, we have 0 of the light component in this steam introduced. That's why we hit the x-axis to achieve this condition where y equal to 0. So we don't have any light component in this steam, hot steam introduced in the bottom of the column. Okay, so this is the reason of doing such a thing. Okay, and so that's it. Now the last point that I would like to cover in this video is the efficiency. And when we talk about the efficiency, we have two types of efficiencies. We have the overall efficiency, and we have the plate efficiency. Okay, what's the difference between them? Let us call the overall efficiency this efficiency cap, for example, and this efficiency is only efficiency. Just it is a simple. Okay, so when we say like this efficiency with a cap, it means the overall. Okay, what's the definition of the overall efficiency? The overall efficiency is simply the number of theoretical stages over the number of the actual reality stages. Okay, what do we mean by theoretical stages? Theoretical stages mean the stages determined from the theoretical approach. It means that using equations and charts. For example, it is the stages determined using the McCabe Thiele method. The stages determined using the McCabe Thiele method. Okay, or for example using the Ponchon-Savarite method that we are going to talk about this method in the next video. Okay, so this number of stages obtained from this method, you see from this method, when we have 1, 2, 3, 4, 5, these stages we can call them the theoretical stages. And to determine the actual number of stages, we need to use an efficiency value. This value usually determined using some calculations that we are not going to cover in this course. Usually it will be covered in the equipment design course. But suppose if it is given, for example, a 90% efficiency, so you get, for example, from the chart using the McCabe method or any other method, you got, for example, number of stages is 5. So you will see that 0.9 is equal to 5 over the number of actual stages. So this will go this. Okay, so you will have the number of actual stages is equal to 5 over 0.9. Okay, and then you're gonna get a number. For example, if you get, just for example, if you get 6.5, there's nothing called 6 and 5 stages, so you can round it up. For example, let's say it is 7. Okay, because you cannot have a half plate, for example, a half stage. Okay, so this is the concept of the overall efficiency. Now let me talk about the other type, which require more work, which is the plate efficiency. What do we mean by plate efficiency? Remember that we say that distillation column consists of too many plates, and each plate we assume, let's focus on one plate where we have vapor going up and liquid going down, and we assume that equilibrium is reached. Equilibrium, which is the final state where each of the light and heavy component know his position, whether in the vapor phase or in the liquid phase. So it is like a static state where you don't have any tendency to disturb this state, so the composition will remain constant. But can we achieve such a stage in reality? Actually, it is very difficult to achieve the equilibrium state in reality, and we can approach this equilibrium state. So for example, if here you have, this is your initial state, and this is your final state. So to reach the final state, okay, you need to be 100%, you need to be 100% efficient to reach this final state, which is the equilibrium stage. But this cannot be reached in reality because we are not efficient. We have too many sources that disturb the equilibrium. For example, changes in temperature, changes in pressure, changes in flow rates, any surprising disturbance that disturb the stages and the flow rate in each stage. So that's why it's difficult to reach this equilibrium static state. So we are going to go close to this equilibrium, for example by 90%, by 80%, etc. And this percentage will be determined per each plate. So it is not overall efficiency. The overall efficiency that we have just discussed is for the all stages, where you just have the theoretical number of stages and you have an overall, so you divide them to get the actual stages. Now we are going to work on each plate where we have vapor going up and liquid going down. For each plate it will has its own efficiency, and we will assume that all the plates are identical, so the efficiency for all the plates will be the same. They are identical, they have the same structure, the same type, etc. Okay, just for simplification. Okay, so now we are going to focus on the plate itself, and to determine this efficiency of the plate, this is again using a method called the Murphy, using a method called the Murphy efficiency. This method is not, I'm not going to cover it for this course. I'm going to learn it later in other courses. But suppose now we know the efficiency. It is determinate because this efficiency will depend on the type of the stage, the type of the plate, whether it is sieve plate, bubble cup plate, etc. We have a valve plate. We have many types of plates. Based on the type of this plate, we can know the value of the efficiency. But now, suppose for this course, suppose you are given the value of the efficiency. Okay, so how you can determine the actual number of stages? Because at the end of the day, we want to determine the actual number, not the theoretical number. The theoretical number is given by the McCabe today method or another method. It's just a number at the ideal conditions where the equilibrium is reached. Okay, so how we can determine the actual number of stages using this Murphy efficiency? One thing that I want to mention here is that this efficiency could be determined in terms of liquid or in terms of vapor. Okay, so we will have two different efficiencies. One is called the efficiency Murphy for the liquid, and the other one is called the efficiency Murphy using Murphy method for vapor. Okay, so it depends on the way that you determine it. But suppose it is given, for example, it is given that the Murphy liquid efficiency is 90%, or it is given that the Murphy vapor efficiency is 80%. How we can use this information to determine the actual number of stages? How we can utilize this information to determine the actual number of stages? How we can utilize this information? First, let's focus on the Murphy liquid efficiency. Then the Murphy vapor efficiency will be the same idea. Okay, so now let's focus on this Murphy liquid efficiency. Okay, so we have a simple equation says that for the Murphy liquid efficiency, xn is equal to xn minus 1 plus efficiency value of Murphy for the liquid times xn star minus xn minus 1. Okay, we have this equation. Let's explain this equation. In order to explain this equation, let's draw a McCabe today diagram. So we have, this is the 45-degree line, and this is the equilibrium curve. And for example, we have this operating curve, we have this screw line, and then we have this bottom section line. And then we start counting the number of stages. So we start here from xd until we reach xw. So this will be 1, 2, 3, 4. Okay, so let me zoom this area. See this area, let's zoom it, this area. Okay, so if we would like to zoom it, I just want to zoom this area. So again, it is this area in yellow. So you will see that you have, this is the stage, and then you hit the equilibrium curve. This is the equilibrium curve, and this is the stage, and then you move down, and of course you have some previous stage, and then you have a next stage. So let me call this stage n. So the previous stage will be n minus 1 stage, and the next stage will be n plus 1 stage. Okay, and suppose I have this axis which is the x-axis and the y-axis. So I am just zooming this area. Okay, I'm just zooming this area. Okay, so what you will see, let's focus on this stage number n. You will see that you have this point and you have this point. Okay, so at this point you have or let's say at this point first, let's focus on this point first. Okay, so we can say that we have a composition here at this point which is yn, and we have a composition at this point which is xn. Okay, you got my point. So we have at this point we will have xn and yn. Okay, and at this point again you will have yn. You will have yn, but for the x you will have a value, different value for x from the previous stage, which is n minus 1. So you will have xn minus 1. Okay, you will have xn minus 1. Okay, so let me call the place where you hit the equilibrium curve, this point. Let me call this point where you hit the equilibrium curve, let me call it xn star. Okay, xn star. So what this equation tell us, it tell us that the actual value for xn, the actual value for x in stage number n is equal to the x value in stage number n minus 1, which is the previous stage, plus the efficiency, mercury efficiency for the liquid, and in the bracket we have xn star. So this is the composition of stage number n that hit the equilibrium curve. So star means it hits the equilibrium curve, and then xn minus 1, which is the composition in stage n minus 1, which is in the previous stage. So in other words, we can say that the actual xn value is equal to xn minus 1. So we see the graph here, we zoom this point. Okay, so what is xn minus 1? This one, right? Which, for example, let's say it's 0.9. Just for example, or 0.8. Okay, let's say it is 0.8. So you're gonna substitute it here. 0.8. Okay, plus, and for example, let's say it was determined that the mercury liquid efficiency is 0.60%. So it's become 0.6. Multiply by, what is xn star? You see here, this point where you hit the equilibrium curve, this will be xn star. Okay, so for example, we read it here, say we get it as 0.6. So we substitute here as 0.6 minus, what's xn minus 1? Again, it's the same as this, right, which is 0.8. So you will get a value here. For example, let's say you get 0.7. So this is the actual, just for example, you get 0.7. So this is the actual xn value. So instead of this 0.6, you will be here 0.7. You will be here 0.7. So the actual point will be here. So you will go to this and then you remove this part. Okay, you remove this part and then you draw the stages like this, starting from this actual point, and then you draw the stages, and then again you draw this, you see, and then remove the extra part using the equation. Okay, and then you continue like this, etc., etc. So you will get another number of stages. This will be the actual number of stages using the mercury liquid efficiency. Okay, now the idea for the mercury vapor efficiency, now let's talk the mercury vapor efficiency. Let's talk about this efficiency. It's the same idea, but the equation is different. The equation is that the actual y in stage number n is equal to y in stage n plus 1 plus the efficiency mercury of the vapor, and then I have yn star minus yn plus 1. It is the same idea, but instead we move horizontally in the mercury vapor liquid efficiency. Here we're gonna move vertically. How? Let's consider again, zoom this part. Okay, let me draw it again. So we have this equilibrium curve, and we have these stages. So this is stage n, our focus. This is the previous stage, and this is the next stage. And again, you have this xy axis, or x axis, and this is the y axis. Okay, so what's the vapor efficiency? Is that you will say that I want to delete this. Okay, so you will say that this actual yn is equal to yn plus 1, which is the value of y at the next stage. So you see, this is the next stage, and this is the value of y, so this will be yn plus 1. Okay, for example, if it is 0.3, for example, so you substitute here as 0.3. Plus, suppose it is determined that the mercury vapor efficiency is 70%, which is 0.7. Multiply it. What is yn star? Again, star, the same thing, refers to the hitting the equilibrium curve, but it is vertically. So you see, we hit the equilibrium curve here, so the value here will be yn star. So you will read it, for example, if it is 0.6, for example, so you will substitute here 0.6 minus, what is yn plus 1? Again, this is the same, which is 0.3. So suppose that you got the actual yn, suppose you got it as 0.5. So you will go and see, where is 0.5? It is somewhere here. It is somewhere here, 0.5. So you will say, I'm going to stop at this point. Okay, I'm going to stop at this point, and then I remove this extra part, and then draw these stages again. And then again, stop here. Of course, we have here the operating line, and then we move up, and then we remove the extra line, and then we continue like this until we count the actual number of stages. So that's it. That's all for this video. Thank you for your listening. I wish you all the best.